case, right? I will upload and give you the links anybody needs. And here is the moon right here. And you can see that, of course, these lines that I have drawn here. So let me remove those lines. So this is actually the sky that you normally see if you go outside and look at the sky right now. And you will not see actually some of these stars, but the brightest ones you should be able to see. Now I am going to add these lines to this chart, which are actually not available right on the sky. You will not see these lines on the sky, right? But when I have these the lines which are connected, which basically connect some of these stars, you can see some patterns here, right? And if you are a little bit familiar with like astronomy, so you can probably identify some of these patterns, right? Now, if you look at this particular pattern, right? Does anybody know what is this pattern? There is a specific name for this one. What is that? Anybody knows from your general knowledge? Right. Now let me add the names of these patterns. Now this one right here, you can see it is called Ursa Major. Right. Now if you go outside and look at towards the northwest direction, you will see this particular star pattern right now outside. If you go outside and if you are in an area that there is not much light pollution, right? Now probably the best time will be during a power cut to see all these constellations. And Ursa Minor is right here, another constellation. Let me see, the Boots is right here. And there is one bright star which we call Arcturus, which is one of the famous stars that you can see up in the sky. And you can clearly see that this particular star is very bright. And if you go outside and directly look at the zenith, so which means that the point directly above the sky, you will see this particular star, right? It is a very bright one, and you can easily identify the star. And there are some other constellations probably you have heard. Now the Sagittarius is right here, which is again a famous constellation, right? Sagittarius is now, if you go and look at the moon right now, moon is in the Sagittarius constellation, right? So that's how you identify some of these constellations. Now, so the reason that I showed you this map and explain some of these patterns, which are we called as the constellations, this is what we will be talking today. And at the same time, there is something extra that I want to show you. If you stay up night, let me fast forward this sky. Now you can see all the stars are moving. Let me see. So I'm going to show you. You can see around now the time is 2049. That means around 2 hours from now, from the eastern sky, there is a planet coming up. So that is the planet Saturn right here, right? Now, something interesting to observe in the morning sky these days is that if you fast forward this again, when it get closer to, so once you just pass the midnight around 1 a.m., there is the second planet that comes into the sky. That is Jupiter, right? Saturn is right here, and next the Jupiter, right? Now let me fast forward this again. Right, so here is the third one that comes, the Mars, right? So the position of planets are here, you can see. Now around 2 a.m. in the morning, if you wake up suddenly and look at the sky, especially towards from the zenith towards the eastern sky, you should see 3 planets actually. Saturn, Jupiter, and Mars. And let me forward this again. Right. So after some time, here comes the fourth one. So that is Uranus right here. I mean, you can't even see that. You can see that the brightness decreases. Uranus is something, a planet that is not easier to observe from the naked eye, right? So you have to have a telescope for that, and the sky needs to be very, very dark. And you can see Saturn is here, Jupiter is here, and Mars is here. Now the Uranus is somewhere here, right? So let me fast forward again, and you can see there is another planet that comes slowly to the sky. So that is Venus, right? Now, which means if you wake up around 5 a.m. in the morning. So let me go and like, yeah, let's say 5 a.m. in the morning, you can see 5 planets on the sky at the same time: Saturn, Jupiter, Mars, Venus, and Mercury. What you can see is also they are on the same line, right? So this is the line that we call as ecliptic. So that is the path of the sun that follows on the sky, and the same path will be followed by all the planets as well. Now, this is a very rare, rare occasion that you can see 5 planets at the same time on the sky. And I can assure you that if you are in a dark area, 4 of these planets should be visible for you very easily. That is Saturn. Saturn sometimes a little bit harder to observe if you are in a place where you have some light pollution. But other than that, you should be able to see Saturn as well. Not the rings of the Saturn. If you need to look at the rings, you probably need a telescope for that. And then Jupiter. Jupiter is easily visible even if you are in a town area. And then Mars. And then Venus. And Mercury. Right. Anybody have any questions? I can hear some of you are talking. If you have questions, feel free to ask. Right, so probably it's a mistake. Yeah. In fact, you can see that the 6 planets are here. The Mercury is also come into play here, right? So which means 1, 2, 3, 4, 5, 6, which means all 6 planets are up around 5 a.m. in the morning. So if you are in a place where you have a very clear skies, a very dark skies, and everything is you can see the whole hemisphere without any disturbances from buildings and everything, you should be able to see like 6 planets, right, out of all the 8 planets. So there are only few that you cannot see here, right? So which is a very, very rare occasion, right? Now this is for today's sky. Maybe this will be more. So Mercury and Venus will be also more up in the sky when it goes to the next week, right? Because they rise like 4 minutes earlier in each and every day. So that's how it works, and you will see why I'm telling that they will rise a little bit earlier each and every day, right? When we go through these lessons, right? So having said that, so if anybody is interested, if the sky is clear, so please feel free to go outside and look at these planets. So that would be a wonderful experience for you as well. Unfortunately for us, from the southern corner, almost all the days are cloudy and rainy these days. So it's very hard for us to, find stars and planets on the sky in these days. Right. So let me stop share this one, and we'll go back to the lessons we had. And something to note here is, let me share my screen. So this is our 4th lecture. So I hope all of you are looking at my screen now. So we basically did an introductory session with the tour of the universe. And on the second day, we again started talking about different sections of the universe in terms of their scales. And then on the third day, we have studied about the birth of astronomy and different coordinate systems that we use to explain the objects on the sky. And there are specific names such as latitude, longitude, and where is your zenith, those kind of things, right? So make sure that you understand those. And today we are going to talk about constellations and ancient astronomy. And so let me share the slides with you. Probably. So as far as I remember, this is where we stopped last time. And let me start sharing the slides. So just give me a minute here, just reauthorize this. And you can probably look at as usual, once I launch the presentation, there will be a code. As usual, you can use that code right here. So you just go for the site called joinpd.com and then type the code NCSIFU, which will give you the slides, right? So make sure that you log in and take the slides to your screen, which will be easier for you to interact with the lectures, right? So as usual. Right, actually, I cannot see that none of you are, is that wondering whether you have an issue? All right, I think one of you connected, which means it should be okay. Right, so let me start the class and you will see the code right up there in the top right-hand corner, right? So we actually talked about these sections, different locations of the sky and how stars rotate and what is altitude means, what is attitude means, those kind of things. And let me go into, I think this is where we stopped last time. And I remember I was asking you to figure out the answer for this particular problem. If there were no clouds in the sky and we were on a flat plane with nothing to obstruct our view, how many stars we could see from our unaided eye. What is the answer actually for this one? Let's look at the answers. Right, so most of you are in between. One has said 0 and 5,000. Actually, the answer is let me directly give you the answer for this one right here. So if there are no clouds in the sky and we were on a flat plane with nothing to obstruct, on average, you should be able to see around 3,000 stars with unaided eye. So which means from your naked eye, you should be able to see around 3,000 stars. Can you believe this? Now, the reason that you don't see this much of the stars are different reasons. Either the sky is not clear, you have clouds in the sky, or you are in a place where the light pollution is high. So that the darker the area, the dark skies make the sky really beautiful, and you will see large number of stars, right? So that's how it works. And you know, when ancients look at the sky, and they didn't have any much light pollutions as we have today, so they found groupings of stars that made some familiar geometric patterns. Now this is what you have seen in my previous map of the sky, right? So there are certain geometric patterns for group of stars that they have found, right? And actually, this was very helpful for them to navigating among the stars. So when you find patterns, then it is easy to navigate through the sky, right, and find the other stars. So that was one of the major uses of these star patterns, right? Now, some of these older star patterns, I have given the names here: Big Dipper, Little Dipper, and Orion, or the Hunter. Right? So you probably have heard some of these patterns, and these are also called as constellations, right? However, the many of the stars that we see are not part of a distinctive star pattern at all, and the telescope reveals millions of stars too faint for the eye to see. Actually, when you look at the sky through a telescope, you will see not like 2 to 3,000 stars, you will see millions of stars that are too faint for our eyes to see. And these stars actually do not make any patterns, right? Now, can you answer this question? So I have given you answers. These are actually just for your general knowledge, right? And this may be helpful for you when you come into the final stage of the course, because you have some kind of general knowledge as well to answer questions. What is the constellation you see in this above picture? So can anybody identify this constellation? Right. So I have given you a few names, and if you are familiar with night sky, or if you have seen this pattern, you should be able to identify it, easily. So I can see 2 responses. How about the others? So these are just for you to get an idea, right? So assuming that this is a part of your night sky, then you see a constellation. So I will just give you 1 minute for this one, right? Not much time. Right, so all 3 who have responded identified this as the Orion constellation, right? Which is in fact the correct answer. And I can see 5 of you have identified it. And right, so everyone is answering that it is the Orion constellation. So good. So I can see that at least few of you have a general idea about that constellation. And here is the Orion constellation, right? You can see these 3 stars right here are called the belt of the Orion. So we call that Orion belt. And this star right here, you can see it's in a different color, right? So this particular star, it's kind of a yellowish red color that it appears right here, while all the other stars seems to be in blue color in this image, right? Now this particular star has a specific name, and this is called Betelgeuse star, and it's a specific star which is a relatively older star and a huge red giant star as well. And you will understand why it is in a different color when we talk about the evolution of stars, right? Actually, the color actually represents the temperature of a star as well. Basically, this particular star is, a little bit cooler compared to these blue stars, and you will understand why when we talk about the evolution of the stars. Right, now if we go back to the lesson again, now when we remember, these ancients had these different patterns on the sky. Now what astronomers did was they form and establish a formal system to organize the sky using these constellations, right? So what they have done is they have defined 88 constellations in the sky, right? Both in the southern hemisphere and the northern hemisphere. Now we have a standard that means there are 88 constellations we used to have, and this is documented and it is available in the web, right? And there are actually a different term called asterism. This is to denote a noticeable star pattern within the constellation. So the constellation is the large unit, and inside that constellation, there are noticeable star patterns as small units. And these small units are usually called as asterism. Now, if I take an example, Big Dipper is actually an asterism within the constellation Ursa Major, right? So if you remember that I showed you the constellation Ursa Major at the beginning, and that's why I showed that to you. And that Ursa Major is a constellation, and inside that constellation, there is a small part that we called as a Big Dipper. Now, Big Dipper is not a constellation in that sense, it is an asterism. It's like a subset, that constellation Ursa Major, right? Right, so I am not going to talk too much about the constellations because this is for your general knowledge, just to get a general idea about the constellations and how they appear on the sky. Right, now let's go back and look at, before we start talking about the modern astronomy, let's look at how astronomy is developed and how astronomers contributed to the development of the science actually. And excuse me. Now, we all know that Earth is a round object, right? We don't believe that Earth is flat. Of course, there are still people who used to think that the Earth is flat. But this is one of the questions that ancient astronomers had, whether the Earth is a spherical shape or whether it's a flat, right? Now, Aristotle actually cited very convincing argument to state that Earth must be round, right? And so what he observed, or his logic is that if you look at the lunar eclipse occurs, what happens is the moon moves into and out of the Earth's shadow, right? Then you can see the shadow that cast on the Earth, sorry, cast on the moon, right? Now, when the moon enters or emerge from Earth's shadow during an ellipse of the moon, the shape of the shadow seen on the moon is always round. Now, if you have seen, please make sure that you connect these ideas with your experiences that you had with these eclipses, right? And if you haven't observed one, make sure that you observe the next lunar eclipse and check whether these things are right? So these are, you can see that these are very, very simple things, but still the science inside that is something that we have to think about, right? Now, this picture shows you a series of images taken during a lunar eclipse, and you can see that how the shadow covers little by little, and once it is completely covered, you can have this red moon, and then again when the shadow goes away, then you can see little by little it goes away. Now, none of these images you cannot see all these, the shadows are curved, right? You can see each and every shadow is curved very clearly. Now, this shape tells you that Earth, this is the shadow of the Earth, by the way, right? So the shadow that you see on the moon is always round during during a lunar eclipse, right? Which tells you that Earth should be a round object, right? Now, can anybody think about if Earth is flat, what will happen to this shadow at one point, at least? What would be what you will observe uh, during a lunar eclipse at one point? If Earth, let's say if Earth is flat, what you will observe? Anybody have any idea? Now just think about, now this will be an exercise, good exercise for you to do it yourself also. If you just think about any flat, let's say a flat plate or something like that, and look what happens if you uh, you know get that shadow onto another round object at a certain point. At some points you will see, instead of curve you will see a line, right, uh, on the other object. So what that means is this particular uh, the object that belongs this shadow is not a round object, so it may be a flat object, so that you will see a line instead of a curved surface at some point, right? So that is the difference between a round object and a flat object, right? So this is what Aristotle used to uh, prove that Earth is a round object, right? So these are, so I am not going to go talk with you the whole history with all the details, but what I have picked here is some of the science they did at the ancient time to prove some of these observations, right? So there is something that we have to get out of these specific observations, right? Not even this one. Actually, the Greeks actually at that time, they knew the earth was round, and at the same time they were able to measure the size of the earth. Now to measure the size of the earth, they have this understanding that the source that is at infinite distance, the rays travel along parallel lines, right? Now this is something that we connect to building telescopes as well. You can see the point A, which is very close to the Earth, these two lines that it dive starting from an A and then it diverges, and this angle is larger, right? Now when you go far away from point B to the point C, this angle getting smaller and smaller, right? Now what happens is when you go to infinity, this angle will become zero. So that means the lines will become parallel. We now know that the sun is at around 150 million kilometers away from the earth, but given that huge distance, you can actually assume that these two green rays are parallel to each other. You can see the reason, right? When you go far and more away from the earth, the angle gets smaller and smaller. When it is a huge distance, like the distance to the sun, this angle is negligible, which means the two lines will become parallel, right? So this is something that they knew at that time, and using that, they have measured the size of the earth. And so I have the story here. I will brief you how they measured the size of the earth. Now, if you assume that all these lines, which are yellow lines that has the rays coming from the sun, we assume that all of them are parallel, right? Now, if let's say on a particular day, let's say on the first day of the summer, for this particular location, right? So you have a well, and this parallel ray will directly go directly like incident on the bottom of this well, right? And the angle is 90 degrees right here. And if on the same day, if you look at the light rays coming into a different location of the Earth, now here it's a kind of a distance away from this particular city, let's say a different city, right? Now you assume that these rays are parallel, but when you look, when it is incident on the Earth, you have this small angle theta, right? Now the only reason if the rays are parallel, they are coming from such a large distance, the only reason that you can have this angle right here is due to the curvature of the surface, right? So that's what they understood. Now, when you if you know the distance between the two cities and the angle right here, you can actually measure the size of the Earth, right? So that's what they have done. I think you can understand how they have used this method to measure the size of the Earth, right? So you can also read the slide which I have mentioned, how you can, assume the size of the Earth from this method, right? Now, from that point of view, we will come into a little bit towards more modern science. Still, it's at the ancient time, around 150 BCE, Hipparchus measured or took the measurements of 850 stars, and he made a star catalog, right? Now, 850 stars. And actually, not only he made this catalog, there are different parameters that he was able to measure at that time. And he divided these stars into apparent magnitudes according to their brightness. So basically, he compared the brightness of these stars and assigned magnitude values at that time. And this one we called as the apparent magnitude, right? As that basically means the magnitude as he observed. Basically, this magnitude is related to the brightness, right? And apart from this, he actually made another remarkable discovery. So that is, the position in the sky of the North Celestial Pole had altered over the previous century and a half. Now, if you remember when we talked about this coordinate system, we basically told that the North Star is fixed. Right? North Star is very close to the North Pole. And then you look at the sky with respect to the North Star most of the time. And if you look at, as it is mentioned here, if you look at the celestial North Pole, we assume that it will not change, right? So you can measure everything with respect to that. But the truth is, Hipparchus found that the position of this North Celestial Pole has changed over the last 150 years when he was measuring or observing this, right? Now, today we understand the direction in which Earth axis pointers need change slowly but regularly. Now we understand that this direction of the Earth axis keeps changing very slowly, right? Which means during our lifetime we will not feel it, but actually changes over the time. And this little change has a specific name, and that is called as the precession of the Earth, right? Let's see this particular diagram right here, which nicely explains the precession of the Earth. Now see that this is the North Pole, and the Polaris, so the North Star is almost directly above the North Pole. And what happens due to the precession is, now precession means the this axis will change over the time. So what happens is this axis will follow this particular path over the course of 26,000 years. So it will take 26,000 years to complete this particular path, right? And this is called precision, right? Now, we know that now our North Star is Polaris, but you can see that after, let's say after 13,000 years, the North Pole will be pointed towards this direction, right? After 13,000 years, which means our North Star will be not the Polaris. After 13,000 years, our North Star will be Vega, right? Which means you can see that even though we use this right ascension declination coordinate system, it keeps changing little by little over the years. But during our lifetime, we will not feel it because you can see that the half of this circle, it takes 13,000 years, which is a large amount of years compared to our lifespan, right? So that's why we don't feel it, but it keeps changing little by little, right? Now I have given a question here based on what we have learned about the precision. So that is, which of the following would be the consequence of a precision of the Earth, right? I can see that only 13 of you have logged in again. And there are around 90 students registered. Now the advantage is you can see that students who have joined with lively and answering the questions, they will find it much easier in the exams to answer, right? Because you are learning the content in real time, right? So I'm just making sure that you understand what I am telling here, right? Because we are meeting online now, I need to make sure that you are with me during these lectures. So let me give you like let's say 1 minute. It's 9:40. I will wait until 9:42 for you to make responses. So I can see 2 responses. Right. So I can see 6 of you have responded. So let me look and see. Right. So I can see that most of you have choose answer B, and answer A and C are also mentioned here. So one answer is Earth's motion around the sun, and the answer B is Vega will be our North Star in future. And I can see that most of you have selected that. And that is in fact the correct answer. And you can see if you were actually looking at this particular diagram. So I have mentioned that our North Star is now Polaris, but it will change to Vega after 13,000 years. So basically our North Star will change, right? So that's will be a consequence of the precision of the Earth, right? Right. So let me go into the next question, right? Now that's one of the few of the findings that we talked in ancient astronomy. The first one was that Earth was round, and then they were able to measure the size of the Earth by by understanding that light rays are parallel from the sun. And then Hipparchus made this first star catalog, and he was able to assign this apparent, something called apparent magnitudes, which we will talk in coming lectures. And then he also found that this precision of the Earth, right? So we talked about that. And actually next, there were debates about our solar system in within early, like 17th and 16th centuries. So there was a model that made by Ptolemy, and his contribution was like a geometric representation of the solar system, and he predicted the positions of the planets, right? Now the complicating factor in explaining the motion of the planets is their apparent wandering in the sky, right? Now we know that all the planets move into a certain direction, but the problem is there is something called retrograde motion for these planets, and you will see what that means in the next slide. Because that Ptolemy assumed a stationary Earth, he had issues explaining this retrograde motion, right? And what he did was he actually introduced something called epicycles to his solar system to explain this retrograde motion. Now, first, let's see what this retrograde motion means, right? Now, this is like, remember that we are looking at this, we are also moving around the solar system, and also we are looking at the other planets. This is similar to something like that you are in a car race that competing with other cars, but also you are looking at the other cars while you are competing with them as well, right? So when you look at it in that way, sometimes you will see some of the cars will go past you and sometimes you pass them, like that, right? Now retrograde motion is something similar to that. Now you can see the sun is right at the center and you have the planet Earth in the next orbit. Let's say this is a planet, let's say this is Mars, right? Now what will happen is initially when you are at the point A, you will see the other planet right here. And when you are at point B, you will see the other planet right here at B. So that's okay. But when it comes to the point C, you can see this planet is aligned with you. Now on the sky, you will see it goes from A to B and then come back again to C, right? Now you can see what actually happens is this is because the relative motion, the relative speeds of between the planets, sometimes you pass the other planet, right? So which means then you will feel like that planet goes to the backward little bit. And then again, when it comes to the point D, it's in this particular point, and at point E, it again goes to the same direction, right? Now this backward motion is what we called as a retrograde motion, and you can easily understand what actually happens by looking at this particular diagram. But at that time, because they thought that the Earth is at the center, especially Ptolemy's model, they had to introduce another circle on top of this path of the planet, which they called as the epicycle, right? Now, from that epicycle, he was able to explain why you have this backward motion, right? So this is how he explained, because he had an idea. He thought that the Earth is at the center and Earth is stationary, and with respect to that, all the other planets are moving. So when you think it in that way, there is no way that you can explain this retrograde motion other than introducing these epicycles, right? So that's what they did. So this is basically a model, but we now know that this model doesn't work because there are no epicycles actually on our solar system. But this is how they thought at the beginning, right? Until they realized that Earth is not at the center. Earth is just one planet that goes around the sun like the other planets, and because of the relative speeds, you will sometimes see this retrograde motion, right? So that is the correct explanation, right? So that this is something that we need to understand right here about from the Asian astronomy. And right, so this is probably an interesting question for you. Now I am going to just to connect this ancient astronomy with our day-to-day life. I was wondering whether you believe in horoscopes, right? So the answer should be yes or no, right? I guess this one should be an easier question for you, right? Sorry, now it's here. So I was just asking whether you believe horoscopes or not. Yes and no answer. And I would like to see your responses. I mean, just for fun, right? Otherwise, you will be sleeping at 10 p.m. when I'm doing lectures. Yeah. Interesting. 3 of you said that you believe it, and one said no, and 3 of you are like 50-50, right? So it's kind of interesting. So I'm so surprised to see that only one of you said that you don't believe it, right? Let's see what astronomy has to do with astrology or horoscopes, right? So I thank you for your answers. I can see 9 of you have responded, and I mean, it's kind of, I'm a little bit surprised to see that from a science students like said that. I mean, you are not like 50-50 means, I mean, you are not sure, right? You think that it's right, like there is a 50 chance of, I mean, there is 50 chance for everything to get correct now, right? Right, let me go back to the, so I'm not going to answer for these questions, but I will give you the details that you could think about an answer, right? How this horoscope and the astrology came into play is that ancient people thought that these planets and stars as representative of symbols of the god, right? And other supernatural forces that control their lives. So that was their belief. And this belief came from, actually this astrology, the subject astrology began from Babylonia a long time ago, and this has a very long history, right? And the key natal astrology is the horoscope, and every one of you knows about it, right? So this was the question that I asked you. What this horoscope is actually is a chart showing the position of the planets in the sky at the moment of an individual's birth, right? So that's how you get this mass, I mean, Angaharu and those kind of planets. And then you make a chart about the position of the planets in the sky at the moment of the individual's birth. And then you have a sign like Kobe, which we called as a zodiac sign, right? And this is actually, the sign is based on zodiac sign the sun was in at that moment when you were born, right? So that's how you get this zodiac sign. Now it's hard to imagine how the position of the sun, moon, or planets in the sky at the moment of our birth could have anything to do with our personality or future, right? Now, that's a question for you to think about it. So it's hard to imagine how this position of the sun, moon, or planet in the sky at a particular moment, or at the moment that when you come to this world, can do anything to do with, I mean, whether there is anything to do with your personal life or the future. Now, to add this, here are the zodiac, 12 zodiac signs, right? Basically attached to these constellations. And so the signs of the zodiacs are shown in a medieval woodcut, and there are no known forces, not gravity or anything else that could cause such effects, right? Actually, there are, in terms of physics and astronomy wise as a science, there are no known forces that gravity or anything else that could cause such effects, right? Now, if you take an example from a straightforward calculation, actually, I don't have time. Otherwise, I could calculate you and show using this Newton's gravitational law that the gravitational pull on the obstetrician delivering a newborn baby is greater than that of the mass, right? So that this is the truth, right? I mean, the doctor that you have right near you when you deliver a baby is actually, he's the gravitational pull by him is greater actually compared to the mass, right? I mean, it's an easy calculation. You can take the distance between the baby and the doctor and the mass of the two objects, and then you can take the mass of the mass and then probably the baby, and then you can take the distance and do a simple calculation using F equal G m1 m2 over r squared as physics students, right? And then you can realize yourself that which force is greater. So that's how you make decisions, right? Now let's move into the birth of modern astronomy. Now that is the whole story that I told you today is actually about the ancient astronomy, how they scientifically thought about some of these different things and discovered some of the things for the first time, and at the same time how some of these beliefs that they have came into play, and how can whether they are true or not is questionable, but scientifically you can see that, I mean, there is no effect, right? When we come into the modern astronomy, we cannot avoid talking about Nicholas Copernicus, because he is the first one who introduced this idea that Earth is one of these 6 known planets at that time that revolve about the sun, right? He was the one who actually introduced this idea about the sun-centered universe. Now, this is Copernicus' system. So what we have, he has here as SOL is the sun, and then we have all these other planets, starting from the sun, the Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Now we have the Uranus and Neptune as well, but they were discovered later. And these are the planets now we have. Now, he also deduced that the planet that is nearer to the sun has a greater orbital speed. Now we know that it's true. And from this, he was able to explain the retrograde motion, because you can see due to the different relative speeds, you get retrograde motion for the planets, right? And this is called heliocentric plan of the solar system, which means the sun is at the center and all the other planets move around the sun. Right now, in science, normally you can actually introduce ideas, but the science doesn't depend on just on one person, right? So when you introduce an idea, then the others are going to test it. Now there should be a mechanism to test this idea and prove it to be correct, right? Now from this Copernicus system, where the sun is at the center and all the others planets are moving around it, we have the Mercury as the first planet, and then the Venus, and then the Earth, right? Now, which means if you look from the Earth, you should see different phases of the Venus, right? So that was the idea. Now, if this Copernicus system is correct, then you have the sun at the center like this. And after that, there are two planets, and one of those planets is the Venus, which is next to the Earth, and Earth is the next planet. Now, when Earth goes around, you should be able to observe different phases, like you see in the moon. Now, for example, moon is in the full moon phase in these days, because yesterday was the Poe day, right? But it will go through different phases, like the waning crescent and then the waxing crescent, like that, right? Uh, In the same way, you should see these different phases for the for the Venus as well, because the Venus is right inside and Earth is right, Sun is right here. And when you look from the Earth, you should be able to see different phases of the Venus, right? Now, this is the assumption that they have. But at that time there were no telescopes and the technology was not developed to observe this. So they had this idea that you should have the phases of the Venus. If the Earth is not at the center, then they need to check this, right? And then to check this, Galileo Galilei came with an idea, and he was the first one who developed the first telescope. This is a telescope that he developed, and on August 25th, 1609, he demonstrated this telescope with a magnification of 9 times to government official of the city-state of Venice, right? So this is the first day that we ever had a telescope. And he used this telescope to examine the planets, and he found some interesting results for the first time in the history. So he found there are 4 moons revolving around Jupiter in times ranging from just under 2 days about to 17 days. So that those are actually periods of these moons. And even now, if you have a small 4-inch reflector telescope, you can actually focus it to the Jupiter. And if you look at the Jupiter, you will also see these 4 moons very close to the Jupiter. Right? You cannot see it from the naked eye, but from the telescope, you can easily see those 4 moons. Right? And now Galileo was the one with having this telescope. He is the one actually who carried out this Copernican theory mentioned earlier. So which means he looked at these phases of the Venus and found that Venus go through different phases like the moon. So this actually proved the idea that the Copernicus had about the sun-centered universe or sun-centered solar system, right? Right. Now, this is a great example in science to explain that these new ideas of Copernicus and the Galileo began a revolution of our conception of the cosmos. And it eventually became evident that the universe is a vast place and that Earth's role in it is relatively unimportant. So we were under the impression that we are superior before this finding about the solar system, that the sun-centered solar system. But now with all these discoveries or findings by Copernicus and then the proofs from the Galileo, we now know that and with all these findings, new discoveries that we have, the role of Earth is relatively unimportant in the universe, because we have a very tiny place on the universe, right? The universe is huge compared to us, right? And apart from that, you can see that Galileo was also able to observe the moon's craters and mountain ranges, valleys, and those kind of things from his telescope as well. Now, this finish my presentation about this section. And this is what we have basically talked is actually stop sharing. How ancient astronomers discovered different things, and especially the approaches that they have taken, because there is something that you have to learn from these discoveries, how they thought about those things and how they proved those things, and how the technology developed up to a certain point with these new ideas, right? Right now, I think 10 time is 10:05, so I'm going to stop today as lecture. Actually I was to like